Today, we've got a real engineering detective story for you, pulled straight from a technical paper from 1980. It's all about a mysterious wobble inside the Space Shuttle's rocket boosters, and how figuring it out was absolutely critical to keeping the shuttle and its crews safe.
All right, here she is, one of the most incredible machines ever built, the Space Shuttle. Now, to get this whole thing off the ground took an unbelievable amount of power, and most of that raw thrust came from these two absolute giants strapped to the side, the Solid Rocket Boosters, or SRBs.
But here's the thought that must have kept engineers up at night. What if that violent but controlled explosion happening inside those boosters wasn't so controlled after all? What if the very power designed to lift the shuttle could create vibrations so powerful they could literally shake the whole thing to pieces?
So, to really get a handle on the risk here, you first have to appreciate the sheer scale we're dealing with. We're going to look inside the main part of the booster, which is called the Solid Rocket Motor, or SRM. This is where all the magic and all the danger happens. Get this, 114.9 feet. That's how long the motor alone was, and it was packed from top to bottom with solid fuel. We're talking about a colossal amount of energy just waiting to be unleashed, and it all goes off in a little over 2 minutes. The forces at play are they're almost impossible to wrap your head around.
Now, whenever you have that much fire in that big of a tube, engineers have to worry about a very specific, kind of invisible threat. It's a phenomenon that has a pretty simple name: combustion instability.
So what is it exactly? Well, think of microphone feedback at a rock concert. You know, that piercing shriek that just gets louder and louder and louder. Combustion instability is basically the rocket science version of that. A tiny flicker in the burning fuel sends out a pressure wave. That wave bounces around, and if it hits the fuel just right, it makes the fire flicker even more, which makes an even bigger wave, and so on and so on. It's a feedback loop that can spiral out of control in milliseconds.
And this diagram, this is taken straight from that 1980 paper. It shows that dangerous cycle perfectly. You can see how an acoustic wave messes with the combustion, which in turn pumps more energy back into the acoustic wave. If the energy you're gaining from that cycle is bigger than the energy you're losing, well, you've got a recipe for disaster. So, of course, NASA and the folks building this thing didn't just cross their fingers and hope for the best. Long before they ever actually built the motors, they ran the numbers using the best computer models they had back in the 1970s to see if this instability was going to be a problem.
And the verdict came back. This quote really says it all. The models were crystal clear. The design was solid. The math said the Solid Rocket Booster would be, and I quote, exceptionally stable. No dangerous feedback loop, no problem. This table gives you a little peek at the data behind that confidence. See, the engineers calculated what's called a stability factor for all the different ways a pressure wave could bounce around in there. And for every single one, the result was a negative number. Now, in this world, negative is a very good thing. It means any vibration would just die out, not get amplified. In other words, stable.
So, case closed, right? The computers said it was safe. But this is where our detective story really gets going. Because the final say on a rocket's safety doesn't come from a computer. It comes from the rocket itself. It was time to actually test this thing.
So, based on all those exceptionally stable predictions, you'd think that when they bolted a booster to the ground and lit the candle, the data from the pressure sensors inside should have been smooth as glass. Just a nice, steady, boring line, right? Nope. This is what they actually saw. And that top line right there, that's the mystery. It is not smooth at all. It's this constant low-level vibration, this wobble in the chamber pressure that the computer models swore shouldn't exist. It wasn't catastrophic, but it was definitely there, and it was completely unexplained.
So now the engineers have a real puzzle on their hands. Their job suddenly switched from predicting the future to explaining the present. What was this wobble? Where was it coming from? And the million-dollar question, was it dangerous? It was time to crack the case.
After a ton of analysis, they came to a new conclusion. The good news? This was not that scary combustion instability they were so worried about. The wobble wasn't that self-amplifying feedback loop. Instead, the thinking was that it was more like a flag flapping in a really strong wind. Just the natural, chaotic turbulence of all that hot gas was kind of plucking at the chamber's natural frequencies.
They realized they couldn't just get rid of the wobble. So they did the next best thing. They decided to understand it perfectly. Their whole method was to take that messy, raw signal you see on the left and through a whole lot of analysis, turn it into predictable, organized data, like the chart on the right, which tracks the wobble's strength over time.
And the process was just pure boots-on-the-ground engineering. They gathered data from every single test fire. Then they used statistics to figure out the wobble's average behavior and how much it could vary. From all that, they set up what they called tolerance limits, which is basically a statistical box that defines the safe zone. This became their new predictive model, one based on reality. And with this new reality-based model in their hands, they could finally answer the ultimate question. They now knew the wobble's limits. They could predict how it would behave, and they proved that even at its absolute worst, it was not a threat to the shuttle. The final verdict? Safe for flight. And that right there is the heart of this whole story. The original computer model was wrong, but the engineering process was absolutely right. By digging into a result they didn't expect, they took a mysterious problem and turned it into a known, managed, and predictable part of the system. They made the unknown known, and by doing that, they made the shuttle safe. It really makes you think, doesn't it? This one deep dive into a 40-year-old document shows you the kind of invisible problem-solving that so much of our technology is built on. It leaves you wondering, how many of today's amazing marvels are standing on a foundation of puzzles just like this one, solved quietly, in decades-old data?